Find somewhere comfortable. You don't need to sit up straight or keep your eyes open. You don't need to hold on to anything that's said tonight. Just let the words come and go the way sounds do when you're already half somewhere else. We're not going anywhere quickly. There's no destination to reach before morning. If today was hard, and for so many people, today was hard in ways that are difficult to name, you don't need to process it right now. You don't need to understand it or resolve it. It can wait outside the door. What's here, in this quiet, is something much older and much gentler than the day you've just lived through. Tonight we're going to wander through one of the oldest questions anyone has ever asked. Not loudly, not urgently. Just slowly, the way you might turn a smooth stone over in your hand without needing to know exactly what kind of stone it is. The question is simply this: why does anything hold together at all? Why doesn't everything just drift apart into separate, lonely pieces? It turns out the answer is one of the most beautiful things science has ever found, and it lives at a scale so small that no one has ever seen it directly, only inferred it, calculated it, dreamed it into being through mathematics and patience and decades of careful looking. You don't need to follow closely. You don't need to remember any of this tomorrow. Just let it arrive softly in whatever way it wants to. We're in no hurry tonight. Somewhere in Greece, roughly 2,500 years ago, a philosopher named Democritus sat with a question that had no answer yet. He was thinking about what happens when you cut something in half and then cut it in half again and keep going. Whether you could do that forever, or whether eventually you would reach something so small that it simply could not be divided any further. He decided you would reach something that could not be cut. He called it an atom, from a Greek word meaning uncuttable. And in that patient, unhurried thought, he started something that would take more than 2 millennia to fully unfold. But Democritus wasn't just thinking about what atoms were. He was also thinking about why they stayed together. Why did some things stick and others not? His answer, which he arrived at through pure imagination rather than experiment, was something close to charming in its simplicity. He pictured atoms as tiny objects with hooks on them and eyes, little loops and catches, so that when 2 atoms came close enough, the hook of one could snag the loop of another and they would hold. Matter, in his vision, was a kind of vast, invisible fabric of latched and interlocked pieces. He was wrong about the mechanism, of course, but he was not wrong about the instinct. There is something that causes atoms to hold each other, something that keeps the world from dissolving. And the fact that he reached for a physical image, something you could almost touch, a hook, a catch, a clasp, tells us something about how deep the question runs. We want to be able to picture it. We want it to feel like something familiar. For most of recorded history, that was about as far as the thinking got. Philosophers speculated. Alchemists experimented and occasionally blew things up and occasionally stumbled onto something real. But the actual interior life of matter, what it was made of and why it cohered, remained somewhere beyond the reach of human understanding, patient and hidden, waiting for tools that hadn't been invented yet. A candle flame is a good thing to think about here. Humans have been watching candle flames, or their ancestors, fires, torches, oil lamps, for as long as there have been humans. There is something in a flame that draws the eye and quiets the mind. People have sat with flames the way you're sitting now, in the dark, in the quiet, and wondered what it was they were looking at. What was burning? What was the light made of? Why did it flicker and move as though it were alive? Nobody knew. Not really. Not for a very long time. What was actually happening inside that flame was a continuous, rapid, extraordinary process of atoms meeting and parting and rearranging themselves, carbon and hydrogen and oxygen finding new partners, releasing energy as light and heat as they did so. Every moment of warmth was atoms settling into new arrangements, finding lower, more restful states, but none of that was visible. None of it was even imaginable for most of human history. The flame was just the flame, beautiful and mysterious and warm. It was only in the early part of the 19th century that the picture began to sharpen. A quiet English schoolteacher named John Dalton, a man who was colorblind and kept meticulous weather records every day of his life and never seemed to be in a hurry. He suggested that all matter was made of atoms, that each element had its own kind of atom with its own characteristic weight, and that chemical compounds were formed when atoms of different elements combined in fixed whole number ratios. 2 hydrogen atoms to 1 oxygen atom, always for water. 1 carbon to 2 oxygens, always for the gas that makes fizzy drinks bubble. Dalton couldn't see any of this. He inferred it from careful measurements of how substances combined and in what proportions, but the picture he drew, atoms as distinct, countable, combinable particles, gave chemistry a foundation it had never had before. Now you could think about matter not as a continuous blur, but as something built from pieces. And if it was built from pieces, you could start to ask how the pieces connected. A century passed. Chemistry grew up around Dalton's idea. Chemists mapped out which elements combined with which, and how many bonds each one could form, and what shapes the resulting molecules took. They learned that carbon was remarkable, able to link to 4 other atoms at once, forming chains and rings and structures of almost limitless variety. They learned that some combinations were stable and lasted for millions of years, and others were fleeting, rearranging themselves almost as soon as they formed. But why? Why did carbon want 4 bonds? Why did some pairs of atoms cling to each other and others not? The mechanism was still missing. The hook and eye image of Democritus had been replaced by something more precise but still not quite explained. Atoms bonded because of their electrons. Everyone agreed on that by the early 20th century. But what exactly the electrons were doing was still unclear. Then, in 1916, an American chemist named Gilbert Lewis published a paper that shifted the whole conversation. Lewis was a thoughtful, somewhat solitary man who did some of his best work sitting quietly at his desk, drawing little diagrams. What he proposed was this: atoms form bonds by sharing pairs of electrons, not by one atom giving something to another, not by hooks and eyes, but by 2 atoms each contributing an electron and holding the pair between them, the way 2 people might clasp hands around the same coin. It was a beautiful idea. It was also, in a way that Lewis himself didn't fully know yet, only the beginning of the real explanation. Because the question of why sharing electrons should cause atoms to hold together, what was actually happening at the deepest level when electrons were shared, still had no answer. That answer was waiting in a mathematics that had barely been written. It was waiting in a new way of understanding the world that was just beginning to take shape. In the early decades of the 20th century, in the hands of a small group of people who were willing to follow the numbers wherever they led, even when they led somewhere deeply strange. The flame still flickered, the world still held together, and the real reason why was still, for just a little longer, somewhere in the dark. Before we can understand why atoms hold each other, we need to spend a little time inside one. Not the textbook version, not the neat diagram with a circle in the middle and smaller circles orbiting around it like a tiny solar system. That picture is tidy and memorable and almost entirely wrong. The truth is stranger, and in its strangeness somehow softer. Take the simplest atom there is. A single hydrogen atom, 1 proton at the center and 1 electron somewhere around it. That's all. The whole universe started with these, more or less, and they are still the most common thing in existence. There are more hydrogen atoms in the observable universe than anything else, by a very wide margin. And yet even this simplest of all atoms, if you could somehow shrink yourself down and stand inside it, would be almost nothing but empty space. The proton at the center, the nucleus, is real and dense and heavy relative to everything around it. But it is also extraordinarily small. If you imagined a hydrogen atom expanded to the size of a large sports stadium, the nucleus would be roughly the size of a marble sitting at the center of the pitch. Everything else would be open space. The electron wouldn't be sitting in a seat somewhere in the stands. It would be a kind of presence, a smear of possibility spread through the entire volume of the stadium in a way that doesn't resolve into a single location until the moment you actually try to find it. That is what an electron is. Not a tiny ball rolling around a fixed orbit, something more like weather, a region of probability, a cloud of presence. At any given moment, the electron is more likely to be found in some places than others, closer to the nucleus, generally, rather than farther, but it doesn't have a precise address. It exists, in a genuinely meaningful sense, in many places at once, until a moment of observation collapses it into one. This is not a failure of our measuring tools. It is not that we simply haven't looked carefully enough. It is the actual nature of the thing. Electrons are not like marbles. They are more like standing waves in a pond, patterns of presence that have a shape and a character, but not a fixed position. And the shapes they take are not random. They are governed by rules, and those rules produce a beautiful, orderly variety. Think of a staircase, not a ramp where you can stand at any height. A true staircase with distinct steps where you are either on one step or the next, and there is no in-between. They cannot hover between steps. They can jump from one step to another, absorbing a precise amount of energy to jump up, releasing a precise amount to fall back down. But they cannot exist at an intermediate height. This is where the word quantum comes from, actually. It simply means a fixed, discrete amount, a step rather than a ramp. The idea that energy comes in packets, in steps, in distinct amounts rather than flowing continuously like water. That was the revolution that changed everything in the early 20th century, and it begins right here, in the architecture of a single atom. Now, the staircase has more structure than just height. Each step is itself divided into regions, different shapes that the electron's cloud of presence can take. The lowest step, closest to the nucleus, has just one simple shape, a sphere. The electron's presence is spread out in a spherical cloud, denser near the center and fading toward the edges. The next step up has more variety, one spherical region and three dumbbell-shaped regions, pointing in different directions. Higher steps have still more complex shapes, some like four-leaf clovers, others harder to describe in everyday language. Each of these distinct cloud shapes is called an orbital, and each orbital can hold at most 2 electrons. These shapes matter enormously. They determine how an atom reaches out toward its neighbors. They determine the angles at which bonds form, and therefore the shapes that molecules take, and therefore, since shape determines function in the molecular world, almost everything about how chemistry works. And here is the part that matters most for what comes next. Not all electrons are equal in terms of their influence on bonding. The ones deep inside, close to the nucleus, are tightly held and largely uninvolved in connecting with other atoms. They're the inner household, you might say, settled and content. It's the outermost electrons, the ones on the highest occupied step of the staircase, the ones held most loosely, the ones farthest from the pull of the nucleus. These are the ones that make chemistry possible. A hydrogen atom has only one electron, and it lives on the very first, lowest step. That step can hold 2 electrons, but hydrogen has only one. So hydrogen has, in a sense, room for one more, a kind of openness. And it is that openness, that single available spot in the outermost cloud, that makes hydrogen one of the most eager participants in the chemistry of the universe. There is something quietly moving about this picture if you sit with it long enough. Every atom in existence is not a solid, bounded thing. It is more like a soft region of tendency, a place where matter is more likely to be found, fading gradually into the surrounding space, with no hard edge, no clear border where the atom ends and emptiness begins. The world at this scale is not made of marbles touching each other. It is made of overlapping presences, of clouds meeting clouds, of probability merging with probability. And out of that soft, uncertain, cloud-like world, something astonishing emerges: stability, order. The solid feel of a table, the wetness of water, the warmth of a body. All of it resting on a foundation that, at its deepest level, is not solid at all, just a vast, patient, quantum humming. Imagine two hydrogen atoms drifting in empty space, far apart at first, so far that neither one has any sense of the other. Each one is complete in itself, a proton, an electron, a tiny cloud of presence hovering around a tiny dense center. Separate, whole, alone. Now imagine them drifting closer, slowly. There is no rush in this story. The universe has been doing this for nearly 14 billion years and has never once been in a hurry. As they approach, something begins to happen. The electron cloud of one atom starts to reach into the space where the other atom's cloud lives. The edges of their presences begin to touch, then overlap, then intermingle. And as they do, something changes about the energy of the whole system. This encounter between two hydrogen atoms, the simplest atoms in existence, was the first bond that quantum mechanics ever explained. It happened in 1927 in a calculation carried out by two young physicists named Walter Heitler and Fritz London, working in Zurich. They sat down with the new mathematics of quantum mechanics, which had only just been written, and asked what actually happens at the level of electrons and their wave-like nature when two hydrogen atoms come close enough to interact. What they found was that the mathematics predicted something real and measurable. It predicted a bond. It predicted the correct distance at which the two atoms would settle. It predicted the correct amount of energy you would need to pull them apart again. For the first time, a chemical bond had been explained from first principles, not assumed, not inferred, but derived from the underlying rules of how the quantum world works. So what did those rules actually say was happening? Picture the two atoms drawing close. The electron of atom A is now within reach of atom B's nucleus, and the electron of atom B is within reach of atom A's nucleus. Each electron, remember, is not a fixed point but a cloud, a spread of possibility. And as the clouds overlap, something interesting happens to those possibilities. The electrons find themselves attracted to both nuclei at once. Instead of being pulled toward one center, each electron now has two centers pulling at it. And when a particle is attracted to two things at once and is free to move, it spreads out. It distributes its presence across the larger space between and around both nuclei, rather than being confined near just one. Here is where the key insight lives. When an electron spreads across a larger space, something happens to its energy. This is one of the stranger truths of the quantum world. The more room a particle has to spread, the lower its energy can become. It's as if the electron, given more space, relaxes. The way water, given a larger basin, finds a lower level and rests there. By spreading between two nuclei, instead of being confined near one, the electrons in a hydrogen molecule settle into a lower, more comfortable energy state than either electron had when it was alone. The whole system, both protons, both electrons, taken together, has less energy as a joined pair than it did as two separate atoms. And because everything in nature tends toward its lowest available energy, the two atoms are drawn together. The bond is not imposed from outside. It arises naturally, inevitably, from the electrons finding a more restful arrangement. This is the heart of it. This is why atoms bond at all. Not because of hooks and eyes, not because of some mysterious attractive force between atoms as objects, but because the electrons, in spreading across a shared space, find a lower energy state, and the whole system follows them down into that quieter, more stable configuration. But there's a balance to be found. As the two nuclei draw closer, they also begin to repel each other. Both protons carry positive charge, and positive charges push away from each other. The closer the nuclei get, the stronger that push becomes. So there is a sweet spot, a precise distance at which the energy gained by the electrons spreading out is exactly balanced by the energy cost of the two nuclei being so close together. At that distance, the system is at its lowest possible energy. It rests there. The bond simply settles into place, the way a ball settles at the bottom of a bowl. For a hydrogen molecule, that sweet spot is almost incomprehensibly small, a distance of about 74 trillionths of a meter. But it is exact. It is reproducible. Every hydrogen molecule in the universe, under the same conditions, settles at exactly that distance. There is something deeply calming about that. In all the apparent randomness of the quantum world, there is this, a precise, reliable resting place found again and again by every pair of hydrogen atoms that has ever met. There is an image that keeps coming back when thinking about this. A child standing between two people who both love them and being drawn in by both at once. Not torn. The child doesn't have to choose. They can rest in the space between, held by both, and in that double embrace, something settles that couldn't settle before. That is something like what happens when electrons find themselves between two nuclei. They don't belong to one atom or the other. They belong to the space between, and in belonging to that shared space, they make the sharing possible. Heitler and London's calculation was a landmark, but it was also a beginning. The hydrogen molecule is the simplest bond in all of chemistry. Two atoms, two electrons, one bond. From here the story grows more complex, more layered, more varied. The spectrum of connection, the full range of ways atoms can hold each other, is far richer than any single story can capture. And that spectrum is worth moving through slowly, because it is in that variety that the whole of chemistry, and ultimately the whole of life, is written. Two hydrogen atoms sharing a pair of electrons equally between them is about as simple and symmetrical as a bond can get. Each atom contributes one electron. Each atom pulls on the shared pair with exactly the same strength, and the result is a perfect partnership, neither atom richer nor poorer than the other, both held at the same quiet distance from the electrons they share. But most bonds in the world are not like this. Most bonds involve atoms that are not identical, atoms with different sizes and different pulls on electrons, atoms whose relationship to the shared pair is more like a tug-of-war than a handshake, and the full range of that tug-of-war, from gentle lean to outright theft, gives rise to almost all the chemical variety that makes the world interesting. Think of it as a spectrum. At one end, the equal sharing of two identical atoms, hydrogen with hydrogen, or oxygen with oxygen, or any element bonded to itself. Both atoms pull equally, the electrons sit comfortably in the middle, and the bond is electrically neutral. No side is richer, no side is richer. Move along the spectrum, and you reach something more lopsided. Two different atoms, both holding on to the same pair of electrons, but one pulling harder than the other. The electrons don't sit in the middle anymore. They spend more of their time closer to the atom with the stronger pull. That atom becomes slightly electron-rich, slightly negative. The other becomes slightly electron-poor, slightly positive. The molecule as a whole develops a kind of internal polarity. One end subtly negative, the other subtly positive, even though no electron has actually been transferred from one atom to the other. Water is the most important example of this. An oxygen atom bonded to two hydrogen atoms, with the oxygen pulling the shared electrons strongly toward itself. The result is a molecule that is electrically lopsided, the oxygen end slightly negative, the hydrogen end slightly positive, and that lopsidedness is responsible for almost everything that makes water remarkable. It is why water molecules cling to each other, the positive end of one attracted to the negative end of another, forming the loose, shifting network that gives liquid water its surface tension and its stubborn refusal to compress. It is why water can dissolve so many things, because its internal polarity allows it to surround and pull apart other polar molecules or the charged particles left behind when ionic compounds dissolve. It is why ice floats, which is fortunate for life on Earth, since if ice sank, lakes would freeze from the bottom up and most aquatic life would have found early extinction. All of this, all of the life-sustaining strangeness of water, traces back to the lopsided sharing of electrons between oxygen and hydrogen. Now move all the way to the far end of the spectrum. Here, one atom pulls so strongly on the shared electrons that the other atom essentially gives them up entirely. This is not sharing anymore. This is transfer. One atom loses an electron, becoming positively charged. The other atom gains one, becoming negatively charged. And opposite charges attract, so the two resulting particles, now carrying opposite charges, are pulled toward each other and hold together not through shared electrons, but through the simple, powerful attraction between positive and negative. This is what happens in table salt. Sodium, a soft metal that reacts with water so energetically it can burst into flame, meets chlorine, a sharp, pale green gas that is toxic in large amounts. In isolation, both are hostile things. Together, they are the mild, crystalline substance sitting in a small bowl on virtually every kitchen table in the world. The sodium atom has one outermost electron that it holds onto rather loosely. It's the single occupant of a step on the staircase that could hold two, and it's relatively far from the nucleus, not very tightly bound. Chlorine, meanwhile, has 7 outermost electrons on a step that wants 8. It is 1 electron short of a complete, stable arrangement, and it pulls on available electrons with considerable force. When sodium and chlorine meet, the sodium's loosely held outer electron moves to chlorine. Sodium, now missing 1 electron, carries a positive charge. Chlorine, now with 1 extra, carries a negative charge. And the two ions, that word just means charged atoms, are drawn together by that attraction, settling into a stable embrace. What's beautiful about table salt is what happens next. It isn't just 1 sodium and 1 chlorine that pair up. Millions upon millions of them arrange themselves into a precise, repeating 3-dimensional pattern, each sodium surrounded by 6 chlorines, each chlorine surrounded by 6 sodiums, the whole structure extending in every direction in a perfectly ordered grid. That orderly crystal, the thing you pinch between your fingers and scatter over food, is an expression of the same quantum principles that govern the hydrogen molecule, electrons seeking lower energy. Opposite charges finding each other. The spectrum from equal sharing to complete transfer is not a sharp line with 3 positions on it. It is a continuous gradient, and real bonds can sit anywhere along it. Some bonds are nearly equal, but not quite. Some are deeply lopsided, but not quite a full transfer. The language of chemistry divides this spectrum into categories: shared bonds, polar shared bonds, ionic bonds. But nature doesn't always respect the categories. Nature just follows the energy. And underneath all of it, the same principle, electrons finding the most comfortable arrangement available to them, given the particular atoms involved and the particular pulls those atoms exert. This is what a candle flame is doing, by the way. The carbon and hydrogen atoms in the wax are bonded together in long, quiet chains. When the wax melts and vaporizes and meets the oxygen in the air, those old bonds break and new ones form. Carbon bonding to oxygen, hydrogen bonding to oxygen, and the new arrangements are lower in energy than the old ones. The difference in energy is released as light and heat. The flame is simply matter, rearranging itself into more restful configurations, releasing the excess energy as it does so. Every flicker is a small settling. Every moment of warmth is the universe finding a lower place to rest. There is something in that image worth carrying forward. The idea that bonding is not a struggle, but a settling. Not atoms fighting each other, but atoms finding, together, a state they couldn't reach alone. The variety of bonds, from the equal partnership of hydrogen to the ionic embrace of salt, is the variety of ways that settling can happen, and the richness of chemistry. The millions of compounds, the endless variety of materials, the whole tapestry of the physical world is what emerges when you let that settling play out across every possible combination of atoms. There is a quiet rule at the heart of all of this, and it has no real equivalent in the everyday world. It cannot be illustrated with a ball rolling down a hill or water finding its level. It is genuinely strange, genuinely without precedent in the world of large things, and yet it is responsible for almost all the variety that chemistry produces. Without it, there would be no periodic table worth speaking of. Without it, every atom would behave more or less the same way, and the universe would be a very dull place. The rule is simply this: no two electrons can be in exactly the same state at the same time. That sounds abstract, so let's approach it through an image. Imagine a very old theatre, the kind with individual numbered seats, each one slightly different from all the others. Maybe the angle is a little different, or the distance from the stage, or the view of the left wing versus the right. Every seat is unique in some combination of ways. And in this theatre, there is a strict rule. No two audience members may occupy a seat that is identical to another seat already occupied. Since every seat is at least slightly different from every other, this means each seat can hold at most one person, and two people cannot share a seat even if they both want to. Electrons in an atom are something like this. Each one occupies a state defined by a combination of properties: which energy level it's on, which orbital shape it occupies, and one more thing, a property called spin, which you can think of as a kind of internal orientation, either one way or the other, like a tiny compass needle pointing up or down. Two electrons can share the same orbital only if their spins are opposite, one up, one down. That makes them different enough in terms of their total state to coexist. This rule was worked out in the 1920s by a physicist named Wolfgang Pauli, and it applies to all electrons everywhere, not just in atoms, but atoms are where its consequences are most vivid. Because of this rule, electrons cannot all pile into the lowest energy level and stay there. The first level fills with two electrons, and then the next arrivals must go to the second level. That level fills, and the next must go to the third. Each level has a limited number of orbital shapes available, and each shape can hold at most two electrons, so the levels fill up in a specific, predictable order. The result is that each element, each atom with its particular number of electrons, has a characteristic arrangement, a specific pattern of which levels and shapes are full and which have room remaining. And it is that arrangement, specifically the outermost, partially filled level, that determines almost everything about how an atom behaves in the presence of other atoms. Carbon has 6 electrons. 2 fill the first level completely. 4 go to the second level, which has room for 8. So carbon's outermost level is half empty. It has 4 electrons where it could have 8. This gives carbon 4 available connections, 4 directions in which it can reach out and share electrons with other atoms. 4 bonds. And 4 bonds, it turns out, is a magic number for building complexity. Carbon can link to 4 other carbons, forming chains. Those chains can branch. They can close into rings. They can carry other atoms attached along their length. The result is a near infinite variety of structures, the entire basis of organic chemistry, the chemistry of living things. Without the rule that limits how many electrons can share a state, carbon would not be carbon in the way we know it. There would be no fourfold reaching out, no long chains, no rings, no proteins, no DNA. The rule that seems like a restriction is actually the source of the richness. Oxygen has 8 electrons. 2 fill the first level. 6 go to the second levels available. 8 spaces, so oxygen is 2 electrons short of a full outermost level. It has 2 available connections. It reaches out for two partners, which is why water is made of one oxygen and two hydrogens, and why oxygen tends to form exactly two bonds in almost every compound it enters. And then there are the atoms at the far end of each row of the periodic table: helium, neon, argon, and their quiet companions. These atoms have exactly the right number of electrons to fill each of their occupied levels completely. Every orbital is full. Every seat in the theatre is taken. There is nowhere to reach out from, no available space to share, no opening for another electron to enter. These atoms sit in serene, complete isolation. They bond with almost nothing. They pass through the world without forming attachments, which is why they are sometimes called the noble gases, a name that carries, perhaps unintentionally, a faint suggestion of aristocratic aloofness. Helium is the second most abundant element in the universe. It is inside balloons and deep-sea diving equipment and the cooling systems of certain medical scanners, and it forms essentially no chemical bonds with anything. It simply drifts, complete in itself, unchanged by every encounter. There is something almost meditative about that. The rule that governs all of this, the one that says no two electrons can be in exactly the same state, was a profound discovery because it explained something that had been observed but not understood. Chemists had known for decades that certain elements were reactive and others were not, that carbon formed 4 bonds and oxygen 2 and helium none. But why? The answer turned out to be this deep structural rule about the nature of electrons, about the fact that they cannot share a state and therefore must arrange themselves in layers, each layer with a fixed capacity, each element's outermost layer determining its chemical personality. The staircase image from earlier comes back here. Electrons fill the steps from the bottom up, 2 per step at most, and it is the highest occupied step, the one that isn't quite full, that reaches toward other atoms. The more empty space on that top step, the more eagerly the atom seeks partners. The more full it is, the less it needs. Every chemical reaction that has ever happened, every bond that has ever formed, every compound that has ever existed, every drug that has ever been designed, every protein that has ever folded, every moment of life that has ever occurred on this planet is shaped by this quiet rule. The rule that forces them into their distinct arrangements and gives each element its character. It is a restriction that turns out to be the source of everything. So far, the picture of bonding has been built on 2 ideas: electrons spreading across a shared space, which lowers their energy, and electrons being forced into distinct arrangements by the rule that they cannot share a state. Both of these are real and important. But there is a third thing happening inside a bond, something subtler and more beautiful, and for a long time it was underappreciated. It has only recently come into clearer focus. To approach it, think about waves. Not electrons yet, just waves in general, ripples on the surface of a still pond. If you drop 1 stone into the pond, ripples spread outward in expanding circles. If you drop 2 stones at the same moment, close together, 2 sets of ripples spread and eventually meet. Where 2 ripples meet, something interesting happens. If a high point of one ripple arrives at the same moment and the same place as a high point of the other ripple, they add together. The water rises higher than either ripple could have managed alone. The 2 waves reinforce each other, building something larger out of the meeting. Elsewhere, where a high point of one meets a low point of the other, they cancel. The water stays flat, undisturbed, as if neither ripple had passed. Electrons behave like waves. This is one of the stranger truths of quantum mechanics, and it is not an analogy or a simplification. It is how electrons actually behave. They have a wave-like character that allows them to do exactly what water waves do: reinforce each other in some places and cancel each other in others. When 2 atoms come close and their electron clouds begin to overlap, the electron waves from each atom enter the shared space between the nuclei, and in that space they can reinforce each other. building a region of higher electron presence between the two nuclei, a denser cloud of shared charge. This reinforcement, this mutual building up of the electron wave in the bonding region, turns out to be one of the most important things happening in a covalent bond. Think of two singers standing in a room, each singing the same note at the same pitch. Their voices are sound waves, and when they sing together in the same key, the waves reinforce each other. The sound fills the room more fully than either voice could manage alone. There is more presence in the shared space, more warmth, more resonance. This is something like what happens when electron waves reinforce each other between two nuclei. The bonding region becomes richer, denser, more present, and that density of electron presence between the nuclei is what holds them together. For a long time, the dominant explanation for why covalent bonds form focused on the energy aspect alone, the idea that electrons spread out and lower their energy by occupying a larger space. And for the simplest bond of all, the hydrogen molecule, that explanation does most of the work. The spreading out and the energy lowering are real and significant. But research published in 2020 examining bonds between heavier atoms, atoms with more electrons, more complex internal structure, found something that shifted the emphasis. For these heavier bonds, the constructive reinforcement of the electron waves is actually the more dominant factor. It is the building up of the electron wave in the bonding region, more than the simple spreading out into a larger space, that is doing the most work to hold the bond together. This matters because it means a bond is not just about electrons being in two places at once. It is about those electrons, in their wave-like nature, actively building something together in the space between the nuclei. The bond is not an absence of repulsion overcome by attraction. It is a construction, a wave structure built jointly by the electrons of both atoms, richer and more stable than anything either atom's electrons could build alone. The image of the two singers is a useful one to carry. When their voices are in harmony, the room fills differently than when only one is singing. You can feel the difference, even if you can't describe exactly why. The sound has more body, more presence, more staying power. Something is built in the shared space that wasn't there before, something that neither voice created alone. This is what quantum reinforcement, that phrase used once and then set aside, means in the context of a bond. The electron waves, meeting in the space between two nuclei, build a presence there that holds the atoms together, not through hooks, not through attraction alone, but through the wave-like nature of electrons and the fact that waves, when they meet in phase, make something larger than themselves. There is something quietly astonishing about this. The solidity of the ground beneath you, the warmth of the blanket over you, the structure of the walls around you, all of it ultimately resting on this wave-like reinforcement happening at a scale so small it makes a single grain of sand look like a continent. Waves building on waves, in the dark interior of matter, holding the world together through nothing more exotic than the fact that they are in harmony. And yet the story goes one layer deeper still, because even this picture, electrons as waves, reinforcing each other, building a shared presence, may not be the deepest truth of what a bond is. There is a more recent understanding, and it is the strangest and most quietly beautiful of all. There is an idea in quantum mechanics that Einstein famously found troubling. He called it, in a letter written in German, something that translates roughly as spooky action at a distance. He meant it as a criticism, a way of pointing out what seemed to him an absurdity in the theory. But it turned out the absurdity was real. The universe actually works this way. The idea is called quantum entanglement, and the simplest way to approach it is through an image. Imagine two coins. You flip them both at the same moment and they land, one here, one across the room or across the city or on the other side of the world. Normally, what one coin does has nothing to do with what the other does. Each is independent. But now imagine a special pair of coins. coins that have been prepared together in a particular way so that they are linked. When you flip them, they always land on opposite faces. Always. If one lands heads, the other, wherever it is, has landed tails. Not because one sent a signal to the other, not because they communicated, but because they were prepared in a state where the outcome of one is always correlated with the outcome of the other, no matter the distance between them. This is entanglement. Two particles prepared together in such a way that their properties are correlated, deeply, inextricably, in a way that cannot be explained by saying they each carried hidden instructions from the moment they were prepared. The correlation is real, and it persists across any distance, and it has been tested and confirmed in experiments many times over. For most of the history of quantum chemistry, entanglement was understood to be a fascinating property of carefully prepared particles in laboratory settings, something to study, something to potentially use in computing or communication, but not obviously connected to the everyday chemistry of molecules and bonds. That changed with research published in 2026 by a team working in Munich in collaboration with a colleague in Spain. What they proposed, and backed with careful mathematical analysis, was that entanglement is not merely present in chemical bonds, it is the deepest explanation for them. The electrons in a bond are not just sharing a space or reinforcing each other's waves, they are entangled. Their states are so thoroughly linked that you cannot describe one without reference to the other, even in principle. Think about what that means. In a bond between two atoms, the two electrons involved are not independent particles that happen to be near each other. They form a single, joint state. The question of which electron is in which part of the bonding region or which direction its internal orientation is pointing cannot be answered for either electron separately. The two electrons are, in the most literal quantum mechanical sense, one system. Their identities have become intertwined. The Munich team developed a framework for describing this, a way of identifying, for any bond in any molecule, what the pattern of entanglement looks like. And what they found was that this framework could describe not just simple two-atom bonds, but the more complex bonding in larger molecules, the kind of bonding seen in benzene, a ring of 6 carbon atoms where the electrons don't belong to any single bond, but are spread around the whole ring in a shared, collective arrangement. Even the fleeting, transitional bonding that happens during a chemical reaction, the moment when old bonds are breaking and new ones forming, could be captured in this language of entanglement. This is a significant shift in how chemists think about what a bond is. For most of the 20th century, a bond was understood as a shared pair of electrons, a useful, concrete, almost physical thing you could draw as a line between two atoms on a diagram. But the deepest truth underneath it, according to this newer understanding, is not a shared pair, but a shared quantum state, an entanglement that makes the two electrons, and through them the two atoms, genuinely inseparable in their description. It is worth pausing on something that this research acknowledges openly, because it is one of the more quietly humbling facts in all of science. Despite more than a century of quantum mechanics, despite the extraordinary precision with which chemists can predict the properties of molecules, despite the fact that the mathematics of bonding is well enough understood to design new drugs and materials from scratch, despite all of that, scientists still debate what a bond truly is. A universal definition, one that everyone agrees on and that captures every kind of bond in a single, coherent picture, does not yet exist. Different mathematical frameworks for describing molecules, and there are several, each with its own strengths and its own picture of what is happening, give different accounts of where bonds are and what they consist of. They agree on the predictions. They agree on the energies and the distances and the shapes. But they disagree, sometimes profoundly, on the underlying story. And perhaps that is right. Perhaps a bond is not a thing at all, in the way a stone or a table is a thing. Perhaps it is better understood as a relationship, a pattern of correlation between electrons, a way of seeing the connections within a molecule that is useful and illuminating, but not quite the same as a physical object you could hold in your hand. There is something freeing about that if you let it settle. The bonds that hold the world together may be less like physical hooks, Democritus's ancient image still lurking at the back of our intuitions, and more like the relationships between people, real, consequential, capable of being described and measured and predicted, but not quite reducible to any single material thing. What it is, at the deepest level, remains a kind of open door. And open doors, in science as in life, are not failures. They are invitations. They are the places where the next understanding is waiting, patient and unhurried, the way the quantum world always is. Somewhere inside you, right now, as you lie still in the dark, something extraordinary is happening. Not one thing, millions of things, billions of things. Chemistry on a scale that makes the largest cities look simple. All of it taking place in the quiet interior of your body, in the dark, without your knowledge or direction. The same quantum principles that hold two hydrogen atoms together in the void of space are at work right now in every cell of your body. The same tendency, electrons seeking lower energy, finding shared space, reinforcing each other's presence, becoming entangled in their quiet way, is the mechanism behind every process keeping you alive at this moment. Consider the proteins. Your body contains tens of thousands of different kinds, each one a long chain of smaller units folded into a precise three-dimensional shape. The folding is not random. It is determined by the bonds within the chain, some strong, some gentle, some no more than a soft electrical lean between one part of the molecule and another, and the shape that results from all those bonds is the protein's identity. A protein that folds differently is a different protein with a different job or no job at all. Right now, during sleep, your cells are folding proteins at a rate that would be difficult to imagine, repairing damaged ones, breaking down old ones that have served their purpose, building new ones for the work of tomorrow. Every fold, every repair, every assembly, all of it driven by the same principles. All of it driven by the same principles. Atoms settling into the configuration that costs the least energy. The universe, inside your body, doing what it always does, leaning towards stillness. And the signals moving between your neurons, the quiet electrical language of the sleeping brain, are themselves a chemistry. The molecules that carry those signals are built from atoms held together by bonds. When a signal molecule drifts across the gap between two nerve cells and locks onto a receptor on the far side, that locking is a bond forming, temporary, precise, shaped by the exact quantum geometry of the two molecules involved. The shape of the signal molecule and the shape of the receptor fit each other, the way a key fits a lock. But the key is not metal and the lock is not metal. They are clouds of electrons, quantum presences, reaching toward each other and finding, in the meeting, a lower energy state. This is how the molecules that soften wakefulness work right now. A molecule called adenosine, a chemical that builds up in the brain the longer you've been awake, accumulating like a slow tide through the day, is binding to receptors in your brain and quieting the signals that would otherwise keep you alert. The bond it forms with those receptors is a quantum event, an electron arrangement finding its rest. And the result is the heaviness you feel in your eyes, the slowing of thought, the gentle pull towards sleep. There is another molecule built in the tiny pineal gland near the center of your brain that rises in the dark. It is made from a simpler molecule, which is itself made from an amino acid your body can't produce without the right food. A long chain of quantum chemistry, step by step, each bond enabling the next. The final product drifts through the blood and tells the body it is night, it is time to slow, and the body, receiving that signal through another bond, another quantum meeting of molecule and receptor, begins to change its rhythm. Deep in each of the cells of your body, in a region so small it can only be seen with the most powerful microscopes, is a long spiral structure carrying the instructions for everything your body knows how to do. It is made of 4 kinds of smaller molecules arranged in a specific sequence, and the 2 strands of the spiral are held together by bonds between pairs of those molecules, each pair held by the same lopsided sharing of electrons that makes water strange and life-sustaining. Those bonds are gentle enough to be opened and read, and strong enough to hold the structure together through thousands of cell divisions. They are, like everything else, electrons finding their rest. The energy your cells are spending right now, even in sleep, even in rest, comes from a molecule that is assembled and disassembled millions of times per second in every cell of your body. It stores energy in a chemical bond, a specific bond between certain atoms in its structure, and releases that energy when the bond is broken. Every heartbeat, every breath, every quiet repair happening in your tissues right now is powered by that bond breaking and reforming over and over in the dark. It is all the same thing. Hydrogen bonding to hydrogen in the void between stars. Sodium giving its electron to chlorine in a crystal on a kitchen table. Electrons reinforcing each other's waves between 2 carbon atoms in a long organic chain. Entangled pairs of electrons holding the shape of a protein together. The signal molecule locking onto its receptor. The energy bond breaking and reforming in your mitochondria. All of it is atoms finding their lowest, most restful state. All of it is electrons seeking the arrangement that costs the least. All of it is the universe doing what it has always done. From the first moment, hydrogen atoms formed in the cooling aftermath of the beginning, leaning patiently towards stability. And you are doing the same thing right now. Sleep is not a pause in chemistry. It is chemistry at its most restorative. The processes that can only happen when the demands of wakefulness have eased, when the body is free to turn its resources toward repair and renewal. The proteins being folded, the memories being consolidated, the cellular waste being cleared, the tissues being rebuilt. All of this is the chemistry of recovery, the chemistry of settling. When you drift towards sleep, your brain waves slow. The fast, jagged rhythms of waking thought give way to something longer, deeper, more patient. The neurons that were firing in complex, rapid patterns begin to synchronize, to move together in slower waves, like a sea calming after a storm. And at the chemical level, the same settling is happening. The molecules that sustain alertness are being cleared away. The molecules that sustain rest are rising. The whole biochemical system is finding its lower energy state for the night. You are, in drifting towards sleep, doing exactly what atoms do. Settling, finding the configuration that costs the least, releasing the energy of the day into the quiet dark and resting in what remains. The hooks and eyes that Democritus imagined, the shared electrons that Lewis drew in his careful diagrams, the wave reinforcement found in laboratories, the entanglement described in the newest mathematics. All of it points toward the same deep truth. Because the joined state is always quieter than the separate one. Because electrons, given the chance, will always find the arrangement where they can rest. And so will you. The day is already somewhere behind you, growing distant. The bonds in every cell of your body are doing their slow, patient work. The universe is leaning, as it always does, toward its most restful state. Drift now, if you're ready. Well.